Okay, good afternoon to everybody, or good morning, or good evening. I don't know where you are today. Okay, now I'm presenting something completely different, something related to surface science and how quantum mechanics, computational chemistry can help to elucidate in some problems connected to surface science, active species supported on other materials, because it's very important to know the structure of these particles. And the interest in this particle, as I will show you, is related to catalytic activity. In particular, my interest is vanadium catalysts that are used for the catalytic reduction of nitrogen oxides. Nitrogen oxides are very bad, very raw particles, because they derive from the combustion or oxidation of fuels from for vehicle, for transport, for from eating. So it's a very present, very contribution to pollution is high, is really significant. So the idea is to find a way to change this particle into something that should be good. Here, in this scheme, okay, is very complicated scheme. The only important point to note is that we start with this oxide, and we want to get, we start from a bad molecule, and we want to get a good molecule, for instance, nitrogen. And this very complicated catalytic process, we see that vanadium is active. Vanadium, sorry, one moment. Sorry, one moment. I went to, okay. And vanadium is vanadium and vanadium complexes are active species for this reduction. We can also see that there is an interplay between vanadium 4 and vanadium 5, that is so the redox active couple that that are the catalyst for this reaction. In particular, vanadium 4 is one electron, unpaired electron, so is magnetic, is a Br spin, and this can be detected by magnetic spectroscopy, like as the electroparamagnetic resonance spectroscopy. And we focus then on how to study and detect these complexes from vanadium 4. Okay, catalysis involving vanadium species depends on a lot of factors: the oxidation stage, the geometric structure, the presence of different kind of complex monomer polymers, the correlation number of the material species, and also because these complexes are not standing alone, because we are speaking about heterogeneous catalysts, are grafted on another material. In this case, titanium dioxide depends also only the surface exposed by the polycrystalline titanium dioxide materials. So to understand the atomic structure of this vanadium species is a serious challenge, because there are lots of factors that should be taken into account. what we titanium dioxide show two preferential faces or surface, one called 101, 001. And now we want to understand how the properties of these vanadium complexes depends on the surfaces on which the species are grafted, and also if this support can promote the formation of monomer vanadium, or eventually also dimeric species. And so we focus on this problem. As I told you, vanadium in this species is vanadium 4. So electroparamagnetic resonance has been used for the detection of this species. And the study is combined with computational calculation from density functional CRDFT calculation, try to exploit, to understand at the atomistic level the properties of this vanadium catalyst. Computational studies are very, very important because they help the understanding of experimental data and then provide complementary information. And together promote the understanding, a deeper understanding of the relationship between structure and properties of this very, very important species. Now, some recap about EPR, electronic parametric resonance spectroscopy. The basic is a phenomenological spin Hamiltonian. There are two components. The first one is the coupling between S is the electronic spin and the magnetic field. Is called the electron-Zeeman effect, and it causes the energy level to be split by the field, by the magnetic field. And but I don't will deal with this part of the Hamiltonian. And the other term is the coupling between the electronic, the spin, the electronic spin, and the nuclear spin. And this coupling is mediated by a tensor, the A tensor. It is called the hyperfine coupling. This tensor is composed by two parts, an isotropic part and an anisotropic part. The isotropic part is called more commonly Fermi contact term, describe the interaction between the Ampere spin, is the density of the Ampere spin, on the nuclei N at the capital R position. And this is very important when the electron is in spherical orbital, because all these kinds of orbital has the non-null probability to have electron density on the nuclei. And then we have the second term that you see, of course, these quantities are a tensor. The second term, B, is describe the interaction between the Ampere electron in valence orbital, P, D orbitals, and it is described within a sort of magnetic dipole interaction, and this is called dipolar interaction. Of course, all these terms, G, GE, GN, are the electron G factor, the gyromagnetic ratio for the nuclei, and mu E, mu N are the electron and magnetic nuclear magneton. Okay, okay. Okay. Now we This is relevant because our system is magnetic. We have vanadium 41, vanadium 4 plus as one per electron, so the spin, the electron spin is 1/2. But also we have nuclear spin, vanadium, hydrogen, oxygen. And so this means that this coupling, this hyperthin coupling between the empire electron and all these nuclei is possible through the hyperthin coupling tensor. So the study of this tensor gives us information about the structure of this complex. The computational approach, okay, calculation we performed using a periodic approach based on a Gaussian type function, basis set, is the crystal code, developed at the University of Torino. I use slab models to reproduce the 100, 101 surface of thick enough to reproduce the property of the surface in a proper way. Also, when we consider the absorption of vanadium, we have an important point is to avoid a contact between these two absorbent space spurious interaction. And so I use a supercell approach. So I use a cell large enough to avoid this spurious interaction. I use the PBA0 functional, hybrid functional that is commonly known to reproduce in satisfactory way geometry and energetics with a good basis set of triple Z quality, so with good basis set. The problem is for the calculation of the A tensor, because for the calculation of A tensor, and especially for the Fermi contact part, is very, very demanding, because we need a good description of the core, the electron core, so the S part of the density of the electron density. So we need a good description of the core of the atoms. At the same time, we need also for the dipolar interaction a basis set that should be flexible enough to take into account this dipolar interaction. So we have to change the basis set, taking account these two requirements. I don't want to go in details with basis set. I use this J basis set developed by Zauer that are Popper basis set modified just to specially designed for a calculation of this coupling constant. Just a remark, the actual calculation of the A tensor is a great challenge for quantum chemistry methods. I also changed the function. I use B3 leap because of course I did a lot of tests and I found that this one is performing better. Anyway, especially when we want to calculate Anatase for transition metal atoms, this is very challenging, because it's not easy to find a convergence in our calculation, to find the best computational setup, because there are compensation between basis set, the choice of the functional. But what we can find anyway are good qualitative agreement, and then this is our target. That is enough, or semi-quantitative, because it's not only qualitative, but is enough to establish trends, correlation between computation and observation. So this is a very challenging problem. Okay, we start with our system. The first point was to synthesize titanium dioxide crystal light that could expose preferentially one of the sources we want to study. There are some procedure for the synthesis of crystal light with preferentially that expose preferentially one facet or another, and this was done. And we have saw two kind of nanocrystallite, one which expose mostly the 001 surface, and other crystallite that expose mostly the 101 surfaces. So we have two different terminations. Okay, on these two terminations, on these two kind of different titanium dioxide crystallite, the vanadium 4 is chloride vanadium 4 vapors was the surface was exposed to the vanadium 4. Here there are the APR spectra. The only thing that I want you to notice that there are here different, the same signal, but with different intensity. That belongs to different species. Species A, more, the signal is larger for this system. Species B is larger for this system. This means that we have two different species because we have different APR signals that are promoted by the two different titanium dioxide surface. Here reported the experimental tensor, also the G tensor, but we don't discuss the G tensor in this presentation. So two distinct species are sorted. And so vanadium 4 can be used to as a probe to correlate the surface structure of these different titanium dioxide termination with the structure of vanadium species, because the spectroscopic indication are clear. Okay, how to proceed now with the modeling? Of course, we considered a lot of possibilities. I reported here the most stable structure among all the unstable structure for supported vanadium. And on the 001, we see that the structure is very similar to square base pyramid. And on the 101, we have a sort of distorted tetrahedral configuration, so two completely different structures. You see also that we can recognize here some geometry parameter, but the most important is vanadium oxygen 1. Vanadium is blue, it's vanadium 1 oxygen 1. It is shorter, and it's clear indication that is for the formation of a vanadyl. Okay, vanadium oxygen with a double bond, different from all the other vanadium oxygen bonds. Also, the implied electron, here is the spin 1, almost 1, tells us it is completely localized on the vanadium atom. Here there is reported a spin density plot almost in a plane of vanadium and the oxygen, neighboring oxygen. And we see that the electron is well localized in the 3D Y orbital. I reported in the case of 001 is the same for the other surface. Okay, now we look at computing a tensor. we look, first we look to the vanadium here for 001 vanadium, okay? We see that we have a large, very large contribution only for one of these components. And this suggests that there is a quasi-axial symmetry, because you see you have a sort of axis of symmetry, quasi-axis of symmetry, okay? And then we look now for 101, we have a similar behavior, but you see there is a larger difference between the 3A value of the tensor, suggesting so a sort of more or less symmetric, more distorted structure. As it is, here we have a pyramid, here we have a distorted tetrahedron. So it is, and also, the value are in a good agreement with the experimental value. We see here a large contribution for one of the value, almost similar to the other two, so axial symmetry, a larger asymmetry for the space P, for the tetrahedral species. Okay, now we consider the tensor computed for the proton. Okay, are reported here. Okay, we see that in the case of the 00 surface, we have a value of around 12 megahertz, this is experimental value, and you see here computed value is very close. For the 101 surface, sorry, for the 001 surface, we have experimental value, the maximum component of the tensor is around 5, computed value is around 4. So this is a very good indication that the structure that coming from EPR consideration is consistent with the calculation, consistent with the observation. So the structure meet the indication derived from observation. The other point we want also to discuss is the oxygen, the tensor for oxygen. In this case, only a sort of average value at this experimental value is derived. If you look at oxygen one is the vanadil. We have a completely different value. It means that the vanadil, so the oxygen moiety, is not the one detected, probably because to the lower abundance of this species, one oxygen with respect to all the other oxygen around the vanadium. It is close to the equatorial oxygen, so the oxygen almost in the plane of the vanadil. And so we think that this can probe mainly this kind of oxygen. But also this is not very fine definition of these components gives us that this coupling is not particularly sensitive to geometric arrangement of the vanadium. I forgot to say about the hydrogen. This value, this good agreement with the computation indicates that these hydrogen are bound to the supported cluster, are not bound to the surface. This is also a strong indication that of the presence of hydroxyl groups and hydrogen bound to oxygen in the supported cluster. And this is a very important point. Now we consider the Dimeric species. In this case, we found that vanadium 4 magnetic is bound through oxygen to vanadium 5 that is not magnetic. if you look at these two distances, vanadium oxygen C, vanadium oxygen 1, this one 1.55, and this one 1.55, tells us clearly that we are considering two different vanadium species. Also, the spin population we have that is localized on one vanadium, and there is a small spin density that is also transferred to the other vanadium, but is a very small amount. So now we look at what we know about the comparison between computed art tensor and experimental art tensor. Okay, we see, we first consider the 001 surface. In this case, we have to consider we have component on vanadium 5. That means that there is a spin transfer from the bonds mediated by the oxygen linking the two vanadium have permitted a bond spin transfer, and this value indicates that almost 3% of the spin is localized over the second vanadium nuclei. The agreement is good for the 00 surface because we have maximum value of 13 megahertz, that is close to the experimental value, computed 13, experimental 14, and the ISO experimental 7, computed 10. So it is good. So the model is really representative of what is measured by APR, so of what is present on the surface. Less satisfactory is the case of the 01 surface, because we have, you see, computed 1, 1, 2, calculated experimental 5 by 7, so it's much larger. Okay, we try to understand what could be the reason. But first of all, one other observation is important. The maximum coupling of order of 3 megahertz, smaller than experimental 7 megahertz coupling, so a quantitative difference that is not negligible, but anyway, is reduced, is consistent with what detected for the 101 sample. So we have on the 101 surface, the value of the tensor are smaller than on the 001 tensor. And this aspect is catched correctly from calculation. Okay, what can be the reason of this larger discrepancy for the 101 surface? Okay, in this case, we consider to try to understand this problem, some mixed valence di vanadium 4-5 complexes displaying different geometries. Allora, in the case A, we have this VO bridging oxygen is in a plane that is almost in the same plane of the vanadium. So this part is almost in the same plane, and the angle is 150. In the case B, in this case, the vanadium oxygen vanadium plane is almost perpendicular with respect to the two vanadium. Okay, this is completely different configuration. In the case C, is exactly the same configuration as found on the surface. What we find when we calculate the coupling in this ABC structure, we see, for instance, we can look at the isotropic, the thermic contact. We see that there is the large difference in the computed value. This means give us an important hint. So that the transfer between these couple, the applied electron from one atom to another, of course, is mediated by the p orbital of the oxygen, and the arrangement of this vanadium oxygen bridge is very, very important, because in some cases this promotes this transfer. In some cases, this transfer is, on the contrary, is not favored. The idea is then that geometrical changes induced on the surface by the local environment can have significant reflection on the observed perfine coupling. What does it mean? That on the surface, we believe that we have this kind of structure, but probably the surface, the presence of some defects nearby, the presence of hydroxyl or water molecule can modify a little bit the structure with respect to what we calculate in our model, ideal model, and this give an hint that, of course, the surface can be more complicated as a catch in these very basic models. So, down the conclusion, the local structure of vanadium are supported on shape engineering to the particle has been studied by means of coupled FPR and periodic calculation. Vanadium grafted on nanoparticles on 001 101 termination can be used as probe to since the absorbed species are different, and so these differences are reflected in the spin-Hamiltonian parameter, as I showed you. Thanks to well-defined nanoparticles with different dominant termination, we were able to assign the spectroscopic feature to paramagnetic vanadium surface and correlate the signal to specific termination. The FT modeling allows to characterize these different structures derived from the experimental indication, and we found that they are completely different. Squared pyramidal for one surface, and the sort of tetrahedron for the other surface. Monomeric vanadium are well characterized by TR spectra. Okay. Other point, the presence of dimeric units has been clearly shown by PR spectra, and also proved, confirmed by the FT calculation, where there is a transfer, a spin transfer, spin density transfer from one vanadium to the second vanadium nuclei. In summary, just to conclude, we provide a robust and reliable description of the nature of structure of monomeric and dimeric vanadium species at well-defined surface, titanium dioxide surfaces, in shape engineered polycrystalline anatase. Evidence is found for the formation of binuclear vanadium for 5 of a complexes, together with the monomeric species. Now, acknowledgement, Professor Mario Chiesa for the PR experiments, Eleonora Romeo for most of the calculation, Professor Maurino for the synthesis of this controlled engineered titanium dioxide nanoparticle.